The topic of this lecture is second-order optimality conditions for constrained problems, and we start the discussion by looking at the case where we have the equality constraints only. In this case, our feasible region is given by equality constraints, and geometrically this corresponds to some type of a surface. When we characterize local optimality properties of a given point, say x star, we need to focus on the local neighborhood of this point on the surface that represents the feasible region. So we are not concerned about this point being the best in some small ball around this point. We only need to consider the part of the ball that belongs to the surface that defines the feasible region. This is the main difference compared to the unconstrained case. And let's recall how the optimality conditions, the second-order optimality conditions, looked in the unconstrained case. In the unconstrained case, we were talking about some kind of local convexity properties when we talked about the optimality conditions. In particular, for the second-order necessary conditions, what we were doing, we were looking at the Hessian of the function. So it was the Hessian of f of x star. And assuming that x star is a local minimum, we said that the Hessian of f in x star must be positive semi-definite. So, and this was the second-order necessary condition. What does positive semi-definiteness mean? By the definition, it means that this product here, so y transpose times the Hessian times y, must be greater than or equal to 0 for any y in Rn. Okay? So for any direction, this must be the case in the unconstrained case. All right? However, in the constrained case, when we talk about the equality constraints, we don't need this local convexity property to hold with respect to every direction, and we only need to focus on the directions that somehow characterize the surface that represents the feasible region. Okay? So what are the directions that characterize the surface representing the feasible region in the best possible way? So these are the directions actually that correspond to the tangent lines to the surface, right? So if we look at the point x star, what directions are the closest to this surface representing the feasible region here at the point x star? So these are the directions that correspond to the lines that are tangent to the surface, right? How do we describe these directions? We can do it using the first-order derivative. The first-order derivatives in this case are given by the Jacobian, and if we think of the feasible region as the level set for the function h at the level 0, so which is essentially what it is, right? So our constraint is h of x is equal to 0. So the feasible region is defined by all points that satisfy this constraint here. The surface defining the feasible region is essentially the level set for h of x at the level 0. So in this case, when we are talking about the level, so we have to realize that this function h of x has m components, right? So this level 0 is actually m different zeros here in one vector. But then what is Jacobian geometrically? So this can be thought of as a vector that is orthogonal to the surface that defines the feasible region in this case. Okay, so this can be thought of as your Jacobian. So then how do we define the tangent lines to the surface at the point x star? So they'll be given by the vectors that are orthogonal to the Jacobian. Then, if I look at some vector tangent to the surface here, so because it must be orthogonal to the Jacobian, so if this is point y, then we must have y minus x star is orthogonal to the Jacobian, so which means that jh of x star times y minus x star is 0. The set of all y's that satisfy this equation here defines the tangent plane to the surface defining the feasible region at the point x star. If we move this tangent plane to the origin, so if you move x star to the origin, right, so then what we'll get will be the tangent space, okay, so the tangent plane will become the tangent space, okay, and the corresponding equation to define it will be the set of all y's in Rn such that the Jacobian times y is equal to 0, okay. We denote this by t of x star, and we call this the tangent space. The tangent space is actually the set that defines the directions that somehow are the closest directions to the surface defining the feasible region at the point x star. Again, because the local optimality of x star only depends on the feasible region, and we are not concerned with the directions that are irrelevant to the surface defining the feasible region, our optimality conditions will change accordingly in this case, all right? So instead of looking at all y's in Rn as we did in the unconstrained case, we will focus on y's that belong to this tangent space. So in other words, we are focusing only on the directions that characterize our feasible region given by the equality constraints. Also, instead of the function f, in the optimality conditions for the constraint problems, we will actually use the Lagrangian, just like we did in the first order conditions. And now, if we replace the function f with the Lagrangian here, so and we'll look at the Hessian of the Lagrangian, so instead of f, now we'll use L of x star lambda, and the Hessian will be with respect to the variable x only. Of course, lambda here is the lambda that we obtain from the first order necessary conditions, right? So because, if x star is a local minimizer for our problem, then the Lagrange conditions must be satisfied, right? If we find this lambda from the first order necessary conditions, then the lambda that we are talking about here must be exactly that lambda from the first order necessary conditions or from the Lagrange theorem, right? And then we look at the Hessian of the Lagrangian with respect to x at the point x star and using the lambda from the Lagrange theorem. And again, we are looking at y transpose times the Hessian times y, and this must be greater than or equal to 0. But now this must be the case only for any y that belongs to the tangent space for our surface at the point x star. So, and this essentially will be the second order necessary condition for the equality constraint problems. As we can see, it's quite similar to the unconstrained one. And again, the differences are that instead of using the objective f of x here, we are using the Lagrangian. And then instead of requiring this positive semi-definiteness property satisfied for all y in Rn, we only require this inequality to hold for y in the tangent space. When we discuss the second order conditions, of course, we require that all functions involved are twice continuously differentiable so that we can take the second order derivatives, right? By nabla 2xx of Lx lambda, we denote the Hessian of the Lagrangian as a function of x. Okay, so we treat lambda as a constant, and we take the Hessian of the Lagrangian with respect to x. So the Lagrangian is what? So it's f of x plus sum for I between 1 and m of lambda i's hi of x, right? And then when we take the second order derivatives with respect to x, we will have the Hessian of f of x plus the sum for I between 1 and m of lambda i's times the Hessian of hi in x. All right. And as we said, the second order optimality conditions in this case will be similar to the unconstrained case. The main difference is that instead of the Hessian of f, we take the Hessian of the Lagrangian, and instead of the inequality for y transpose times the Hessian times y greater than or equal to 0 being required for all y's in Rn, we require it only for y's that belong to the tangent space of our surface at x star only, right? So here we formulate the second order necessary conditions. If a regular point x star is a local minimizer for our problem of minimizing f of x subject to h of x is equal to 0, then there exists a vector of lambdas, lambda 1 through lambda m, such that this essentially states the first order necessary condition here once again, right? And of course, from here, we will find lambdas, the Lagrange multipliers that correspond to this local minimizer x star here. And then we'll need to use these lambdas in the second order condition. The second order condition is that for any y in the tangent space at x star, we have y transpose times the Hessian of the Lagrangian times y is greater than or equal to 0. And next we'll formulate the second order sufficient conditions, which will be also very similar to how it was done in the unconstrained case. Remember, in the unconstrained case, we said that if x star is a local minimizer, then the Hessian of f at x star must be positive semi-definite, right? So this was the necessary condition. And for the sufficient condition, we said that if the Hessian is in fact positive definite, then x star must be a strict local minimizer. Okay, so here it's very similar. So for the second order sufficient condition, if we have a regular point x star that satisfies the second order necessary conditions with lambda equal to lambda star, and if in addition to that, for any y in the tangent space of the constraints for the point x star and y is not equal to 0, we have this product actually is not just non-negative but strictly positive, then x star is in fact a strict local minimizer for our problem. Let's consider some examples of applying the second order conditions. In the first example, we look at the problem that we already solved before. So this was the problem of minimizing the square of the norm of x subject to a single elliptical constraint. So let me remind you how this looked like geometrically. So we had the feasible region given by this ellipse here. This was minus 1 over square root of 2. This was 1 over square root of 2. This was 1 here and minus 1. So this x1, x2. We also had the level sets for the objective, so which were given by circles. So this is the level set for the objective corresponding to the local and global minimizers here, and they were given by the points 1 over square root of 2, 0, and minus 1 over square root of 2, 0, and the corresponding Lagrange multiplier was minus 1/2. And then we also had two maximizers which corresponded to the circle of radius 1. Here we have 1 minus 1, and we had two maximizers, right? The first maximizer was the point 0, 1, and the second maximizer was the point 0, minus 1. All right, so and then the minimizers are given here, right? So, but overall we had 4 stationary points, just 4 points that satisfied the Lagrange theorem or the first order necessary condition. Just by looking at the geometrical illustration, we could see that 2 of these points are global minimizers and 2 of these points are global maximizers. And we can also make this conclusion without even looking at the geometrical illustration. We could just observe that the feasible region for this problem is a compact set. And then since the objective function is continuous by Weierstrass theorem, the problem must have global minimizers and maximizers. And then by the Lagrange theorem, all these local and global minimizers and maximizers must be among the points that satisfy the first order necessary condition. So, and since there are only 4 points like that, by looking at the objective function value at all the 4 points, for 2 of them the objective is equal to 1/2, and for the other 2 the objective is 1. So the 2 points for which the objective is 1/2 are 2 global minimizers, and the other 2 points are global maximizers. All right. So, but now we'll actually show that these 4 points are strict local optimizers by using the second order optimality conditions. For that, what we do, we compute the Lagrangian. Well, we already had the Lagrangian before, right? So let me just write it down here. So it was L of x lambda was given by x1 squared plus x2 squared, and then plus lambda times 2x1 squared plus x2 squared minus 1. All right, so and then if we take the Hessian of the Lagrangian with respect to x, we will obtain, let's look at the second order derivative with respect to x1 first. So we'll have 2 from here, and then we'll have 4 lambda from here. So 2 plus 4 lambda. And then if you take the derivatives with respect to x1 first and then with respect to x2, then we'll get 0. So similarly, here we'll have 0. The second order derivative with respect to x2 and then x2 again will be given by 2 plus 2 lambda. All right, so here is the matrix of the Hessian of the Lagrangian. But now we are not concerned with the positive definiteness or positive semi-definiteness of the Hessian of the Lagrangian overall, right? So, but we only need to make sure that it is positive semi-definite when restricted to the tangent space at the corresponding point, okay? So let's compute the tangent space for the first stationary point, the point x1, given by 0, 1. What is the tangent space? So by definition, we need to use the Jacobian. In this case, the Jacobian is given by 4x1 and then 2x2. So this is our JH of x1. Okay. And now we need to plug in the values for the point x1 instead of x1 and x2, right? So we have 0, 1. So it will be 0, 2. Okay, so this is our Jacobian, and by definition, the tangent space at this point x1 is given by the set of all y's such that the Jacobian, which is 0, 2, multiplied by y, which is given by y1, y2, is equal to 0. Okay, so now what is this equation here that we have? So it's the same as the set of all y's such that 0 times y1 plus 2 times y2 is 0. Okay, so but because we have the coefficient of 0 for y1 and then we have 2y2 is equal to 0, so this means that y2 must be equal to 0 and y1 can actually be anything. So this will be the set of all y's such that y is given by some c and 0 transposed, where c is any real value. Okay, so this is our tangent space, so it's given in the form c0. And then for checking the second order conditions, what we need to do is compute the Hessian of the Lagrangian for the given point. So in this case, we see that the Hessian of the Lagrangian depends only on lambda. We plug in lambda corresponding to this point x1, and lambda is equal to -1. So the Hessian of the Lagrangian at the point x1 is given by -2, 0, 0, -2. Okay, so now if we multiply this matrix by y from the tangent space, we will have c0 multiplied by -2, 0, 0, -2, and multiplied by c0, so which is the same as -2 c squared. And obviously this is less than 0 as long as c is not equal to 0. So we can see that in this case we have the less than 0 product, therefore we have a strict local maximizer. So, and this is exactly what we had for this point from the geometrical illustration also. But in fact, we can also observe that the Hessian of the Lagrangian in this case is given by a negative definite matrix. So this inequality y transpose times the Hessian of the Lagrangian times y is less than 0 for all y is not equal to 0. It holds for any y, including the y's in the tangent space. In fact, because this is the case, we didn't even need to compute the tangent space here. We could just say that, okay, this matrix is negative definite, therefore this is a strict local minimizer. Because for the matrix to be negative definite is actually a stronger condition than saying that this negative definiteness inequality holds for points in the tangent space, right? Anyway, we computed the tangent space just to illustrate how this is done. And we saw that for all points in the tangent space, we have the strictly less inequality, assuming that the point is not 0. Therefore, we have a strict local maximizer here, as we expected. So this was for the first point. For the second point, again, because lambda is the same, the Hessian of the Lagrangian will be the same, right? The tangent space will also be the same, in fact. Therefore, we also conclude that this point is also a strict local maximizer. Similarly, we could conclude that the other 2 points are strict local minimizers by, again, looking at the tangent spaces for x3 and x4. So in both cases, the tangent spaces are given by the set of vectors where the first component is 0 and the second component is anything. And then if we plug in the corresponding lambda values, so lambda was -1/2, then this will be 0 here, and this will be 1. Okay, so then the product y transpose times the Hessian of the Lagrangian times y will be given by just c squared, which is obviously greater than 0 whenever c is not equal to 0. So, and again, by the second order sufficient condition, we conclude that these points x3 and x4 are both strict local minimizers.
That's what I'm talking about!